will start with Vincent Mourik about proton pair spin and solid state quantum devices.
Yeah, good morning. Hello again. So on my walk through this city, which is very empty today, this morning, I saw a beautiful mural, and I think I took a picture of it, and I think it's inspirational for today. Maybe you saw it already. I think it's very fitting that we are on a national holiday, working on our education together. I don't know, this is somewhere on my walk to the city, so maybe we can all seek inspiration from this. Anyway, so today I will actually talk about nuclear spins. Yesterday it was sort of mentioned here and there, not really, but today I'll talk about them. It will take me probably about half the lecture to get to them. I want to connect yesterday's lecture with the specific devices that we use to measure these nuclear spins. Once again, there's this other lecture. I make a big sacrifice. I think I'm the only Dutch person here, and I think I'm going to miss the Dutch game over it this afternoon. But that's okay. This is more interesting, much more interesting, I think. So I hope you all come. So I changed now to black background. That is for the really cool stuff. This is a habit in the group I was part of, the Moreno group at UNSW, that all the slides and posters are black background, so I will stick to that. And I want to acknowledge the entire group, and in particular these people, Andrea himself, but also Arne, Sterwan, and Irene, for providing me with figures and slides that I incorporated in today's presentation. And this covers basically, my talk will cover the 2010 till now era from the research in this institute, and I spent about 6 years of my postdoc there working on this topic. And throughout the talk it will come clear where I sort of sat in there. Alright, so this is now about donors in silicon. Okay? And to a reasonable approximation, you can treat a donor electron of phosphorus in silicon like a hydrogen atom in vacuum. So phosphorus sits next to silicon, it has one more proton, one more electron. And from a band structure perspective, what it does when you put it in silicon is that you have this Coulomb-like binding potential, very steep binding potential. And you have this loosely bound outer electron of phosphorus sitting below in the band here. This is 45 milli-electron volts below the Fermi level. So it's a shallowly, loosely bound electron. And it is, that is the 15th electron. The other 4 form the valence bonds at silicon, and the 5th electron is sort of, wandering around a little bit in the lattice. It has an effective Bohr radius of about 2 nanometers. Okay? And the point is that this system, you can use it. All the inner electron shells are closed. They form singlets, and we don't need to deal with all these electron spins. But this outermost electron and the nuclear spin, this is a 1/2 spin, 1/2 nucleus, we can use and work with. So the whole point is that we can use the electron spin and the nuclear spin both as a individual qubit, and they are coupled through hyperfine coupling. So it's a coupled nuclear electron spin system that we can fully address. And the point of the first half is to make clear how we do that. Okay? Now, what drives this research? I don't want to go into all the fine details of this, but this is an old proposal, I would say, fairly old, from 1998, visionary proposal from Bruce Kane. Actually, he did that during a postdoc, I think, at UNSW, and that is sort of how the entire silicon-based quantum computing research at UNSW got started in Sydney. So the idea is that you build a quantum computer based on donors in silicon. So the physical qubit of choice is the nuclear spin in silicon. And there's a whole bunch of reasons why nuclear spins could be good qubits. They're very coherent, etc., well isolated. Okay, so that is your physical qubit. Those we can, of course, one qubit gate, single qubit gates we get from NMR. So we can, like I explained yesterday, for the electron spins, we can do the same for nuclear spins. That is nuclear magnetic resonance. So we can use that to do the single qubit gates. And then to address the qubit, we have electrical control over the hyperfine coupling, so we need to be able to pull the electron wave function to and from the donor a little bit, and that way turn on and off the hyperfine interaction. And then for 2-qubit gates, we have the exchange interaction between neighboring electrons. So overlap between the electron wave function of neighboring donors that can be controlled with a gate. That is the idea to implement 2-qubit gates. Okay? And for that to work out, you can sort of crunch the numbers and estimate this a little bit. You need to have a resolution of about 10 to 50 nanometers or so of the donors. But it is, in very broad strokes, the blueprint of why people started pursuing single donors in silicon for quantum computing purposes. At the end of the talk, I will comment on this. I think it's not going to work really, or very difficult to make this really a reality. People are still trying it, but it's very, very difficult. But at the level of single donors, or maybe a few donors, you have a really interesting model system that you can do very cool experiments with. That is the point I want to convey today. Very briefly, there's two approaches here that have been pursued, both at USW primarily, I would say. So there is the top-down approach, where you work on a silicon substrate and you use standard lithographic techniques to make a device, and the ions, the donors, are implanted using ion implantation. So there is no precise spatial control of the position of the donor. It is a random process. The ion hits the lattice, straggles a little bit, finds a position. And most of these experiments are done that you have a small dose of these ions, so maybe 10 or 15 of these phosphorus donors sit in the active region of the device. There's efforts in the way that you can do counted implantation, so at least you know that you implanted a single ion, but precise control will never happen because the ion, when it hits the lattice, needs to release its energy, so it straggles a little bit, and you will always have at least 10 to 50 nanometers uncertainty in the position. It's more of a bottom-up approach where you use SDM lithography and you do really local phosphorus doping. Very challenging, but I think really impressive results have been obtained there as well. Of course, this is in principle compatible with the CMOS industry. This is more of a academic style technique, I would say. Maybe I should turn on the light so you can see the slides. Which one is there? That's probably the one. Better? All right. Now, I will really stick to this device design. Okay, this is I would say here the main challenge is device fabrication. Control is starting to happen about now. Like I think first qubits have been demonstrated here. This is sort of 10 years ahead in terms of the control over the donor. So this is the system I will focus on today. And here is where I want to take a step back and connect it back to yesterday's sort of overview talk about spin qubits. How do we operate this device? So the readout, it's the same readout scheme that I introduced yesterday. Okay? So it is spin-dependent tunneling into a charged reservoir. So this is based on K-defined quantum dots in gallium arsenide. You pulse your quantum dot below the Fermi level of a reservoir, then you load a random electron on it. You don't know the spin state, but one of these two spins is loaded. You pulse it in between those two possible states, and then only one of the spin species can tunnel out. In one case, you have a tunnel event, in the other case, it is blocked, and at the end of the sequence, you empty the dot. Okay, and during this phase, you observe this tunneling event, if it happens. So this is the process of spin to charge conversion. And this was the dot that I showed you yesterday, so this is K-defined, and here we used the quantum point contact as the charge detector. Okay, so this one was sensitive to this tunneling event happening. Here we have a similar, very similar, the spirit is the same, but of course the details differ, so I want to talk you through that. So this is the device we use for the readout. We call it an SET, single electron transistor. In a sense, it is a large quantum dot. Okay, so nearby we have implanted a number of phosphorus donors. You can, statistically speaking, there should be about 15 to 20 of these donors in this region. And then There's a local gate here that can address part of these donors, their electrical potential, and typically there is a fuel coupled to this gate strongly. Okay, so in our active area you have typically a number of donors. This is an entirely statistical process, right? Like some devices have too many, some have none, and you need to cycle through a few devices until you find one that behaves the way you want. And this is the SET island, so we have a source and a drain, we have two barriers, and here we form a small island with typically about 50 to 100 of electrons on it. It's not it's size-wise, it should behave like a metallic island, but because it is in a semiconductor, we do see some quantization effects, but it's sort of negligible. Now, the analogy that you can think of is rather than a double dot in series, it's a double dot in parallel. Okay, so we have one quantum dot sitting here, that is the equivalent here, that we measure in direct transport through the channel here, and then there is this second one that is coupled to it. So this is a parallel double dot system. It's a slight variation of what I showed you yesterday. Now, let's look at the energy landscape as we go along this line. So from the area where we have the donors, via the SET island to one of the reservoirs. What we have then, this is the Fermi level in the system. We have the binding potential of the donor with the confined electron state in it. And this is gate controlled, so we can shift this level now up and down, above and below the Fermi level. Then there is a tunnel barrier, typically a fairly wide one, and this is of course uncontrolled. This is a property of the device where the donor exactly sits. And then there is this charge reservoir formed by the SET island, and then we have the source and the drain, and these are tunable tunnel couplings that we can tune with the gate voltages here. Okay. And this acts now as the reservoir that we tunnel into to do the spin to charge conversion. So if we now apply a magnetic field, we spin split the states of the donor, but also so in that case, we have to tune the system such that one of the levels sits below, one sits above, and we can tunnel out dependent on the state of the spin. And then detect that in our readout signal here. Okay, so the typical standard tuning that we use in this experiment is that when the donor is neutral, so when there is an electron on the donor, the current through this channel is 0, and when the donor is ionized, so when the electron has tunneled off, the current through the device is maximal. So we have a discrete difference between the charge states of the donor. No current means donor is neutral, high current means donor is ionized.
Sir,
yeah?
is it important in which direction you apply magnetic field?
For phosphorus, nominally speaking, I would say no. In principle, the direction doesn't matter so much, because the system is almost isotropic. It may matter a little bit for the driving, because that needs to happen orthogonal to the Zeeman. The magnetic field is what provides your quantization axis of the system. And then the way where your driving field, that will come later in the talk, but to do the spin resonance techniques, that is a device property, so it's sort of a fixed effective direction. And depending on the effective magnetic field, I suspect you will get a dependence on the drive strength that you reach, because of the orthogonal component will vary a little bit. But other than that, for phosphorus, things are mostly isotropic in magnetic field.
So here you really purify it perfectly.
It doesn't matter really. Like, I think we apply it in plane. Yeah, I think we mount a chip vertically. For later on in the talk, for other stuff, it will matter a lot, but here not so much. Alright, so another effect that we have, I already mentioned it a little bit, is that we have, of course, the Zeeman splitting of the donor state, but we also have something happening here. This is a many electron quantum dot, so it is a quasi-continuum of states. It's not a proper Fermi-Dirac as you have in a metal, but it's quasi-continuum, so also here there is some Zeeman splitting happening, some orbital level splitting is still present, and all what this means is that you have a quasi-continuum. It's sort of like a wobbly density of states. The states are so poorly separated that it is a quasi-continuum and you can always tunnel, but the tunnel probability will be a little bit energy dependent here on the states in the dot. So we do observe that sometimes in experiment. For the purpose of this talk, you can treat this as a continuum, like it's basically hidden in it's one of the explanations why the data sometimes looks a bit inhomogeneous, etc. Okay? Now, how do we describe that then in an experiment? So we have a coupled donor with two possible charge states, 0 electrons on it and 1 electron on it, and we have this ladder of states that I also showed you yesterday on the island. Now, because of the capacitive coupling here, this ladder of states will undergo a discrete shift dependent on the charge state of the neutral donor. Okay, so we have two possible configurations, the solid line and the dotted line. Now, if you plot that as a function, because we have gates in this device, so we can follow these states in gate space. So this is this is the gate that controls the donors. And this is the gate that sits on top of the island that controls the island potential. Of course, there is some cross capacitance between those two gates, so we don't, when we change this voltage, you will also affect the donor energy level and vice versa. And what you can see here is that these states show up as these bright lines. So this is a schematic, it's a drawing, but in a current map, you have very low current in between, where the system is in Coulomb blockade. So this island cannot conduct current, but then whenever you have one of these levels in resonance with source and drain, you get this current line. But once you are close in energy space, meaning gate space, to the donor charge state, you will get this discontinuity. Okay, so this is a feature of a double quantum dot. And in a proper double quantum dot where you have many states in both levels, this will become an intricate lattice. It will become a honeycomb type structure. But with the donor, we only have this single discontinuity because we have only two possible charge states. Okay, so this, when you observe this in experiment, you know that there is a charged defect, either a trap, a single electron trap in the oxide interface or so, or a donor sitting next to your SET island and tunneling to it. This tells you there's two possible charge states. Now, the amount that you shift here, you can express that in terms of the total difference between the charge states of the SET. So there's a slight delta Q here as a fraction of the total change here that you have between two charge states. And that's a fractional effective electron charge which scales with the capacitance of donor to the island. And yeah, if this is large enough, we can detect it. Okay. Note that there is two tunnel rates, like this is tunable, and this is typically a much higher tunnel rate, so that you can have a measurable current. So this is in the nanoseconds range, this tunnel rate. And this tunnel rate from donor to island is more in the millisecond range. And it's very difficult to tune with gates. It's sort of built in the device. Okay. Now, then we have our spin to charge conversion gain. So, when the donor is neutral, we are sitting over here. We don't have current. We are sitting slightly below an accessible level. And we cannot tunnel out, but then when we put it on resonance at this level here, we can tunnel. Dependent on the spin state here, we get current. So that is when we sit in this position over here, we sit on the line, so we move from here to here. Then you tunnel out, and then at some point, determined by the tunnel time of this tunnel barrier, an electron will tunnel back into the lower level. And because of that, the current will be blocked again. And we move back to this spot. Okay, so we move from here to here and back again. And this is, in this process, we have converted the spin state to a charge. So you either measure or you don't measure a little blip of current. And this tells you what strain state you have. And that's sort of the point of talking about how much you shift here on this line. If this coupling is about 10% or more in terms of this stability diagram, we can detect it. Yeah?
But then you're talking about this detection of spin state. You mean electron spin?
Electron spin.
And
nuclear spin comes later. I'm sorry. I'm sorry. It will be around the break, near the break. One thing to realize is that when you, as long as you don't observe a current, you have not done any action on the electron here of the donor. When you do observe a current blip, it means you have taken out that electron and the electron is gone. As long as it keeps sitting there, you have not performed an action on it. But the longer time runs, the more you learn about its state, right? Like you're slowly projecting it into the red level here when you don't observe current. But then in principle, it stays coherent, you could continue quantum operations on it. Once it is in this state and you observe your current blip, the system is gone and you need to reinitialize. So, this is then of course the actual protocol. We have our pulse where we load, so we start from an empty donor, so we start from high current, we plunge it, we put this level below the level of the reservoir, we get at some point an electron tunneling in over here, so current drops to 0. Then we put it in the read position, and if we were in the purple level here in the spin state above this level here, we will, after a time scale determined by the tunneling, we will observe a little current blip. And then during this read pulse, where we keep the level like that, we will reinitialize the system with the lower spin state. And then in this sequence, typically afterwards, you put the levels entirely above it so that you empty the donor again and you can start from this side. Okay, so this is the sequence: load, read, and empty. And then you can repeat this many times and look at the statistics. Okay, so this is the measurement setup for this particular experiment. So we have a number of gates here that are hooked up to voltage sources so we can control the potential landscape. We have a bias voltage across the island here that is typically of the order of 100 microvolts or so small bias voltage, so that we can measure current. And then we apply this load, read, empty pulse. We apply that to both the stop gate and to this plunger gate that couples stronger to the donor. And the reason for that is if you apply the voltage to a single gate, you can either move in this direction or in this direction, vertical or horizontal in the diagram. But if you apply the right scaling factor, which is essentially a linear conversion factor, because this is pretty much a classical capacitance model that we use here, you can move really along one of these diagonals. Okay? So basically what it means is that you keep this ladder fixed in the same position as you pulse this donor. It allows you to independently tune either of the two sides of the system. Alright, so that is how we move. And then this is what you observe in experiment when you map this out as a function of those two gates. So you see all these bright lines. In color scale we have current, so this is a unit, this is 100 picoamps or so reasonable current, not too difficult to measure. This is all the various SCT states. You can see that they are nicely equi-spaced. That sort of confirms that whole picture that this is a many electron quantum dot. But then you see this discrete jumps in there, in the map. Okay? And this is caused by donors. Although when you measure this, you are not certain yet what it is, because it could also be any other type of charge trap, like a defect at the oxide interface or so, coupled to the SCT will also potentially show up like this. But you know, we know by now that many of these, the majority of these are donors, not all of them. So this is a donor that sits very close to the SCT. It has a fast tunnel rate, it has a large shift in this line here. And this is a pretty fast tunnel rate, 10 microseconds. And here we have one that sits a bit further from the SCT, it's a bit weaker coupled. And you have a slower tunnel rate. And basically the concentration of dopants that you have determines how complex or simple this diagram looks. If you have too many, you will have many crisscrossing lines and it becomes unworkable. You cannot find a nice spot and gauge space to operate. If you have none, this will be just a boring straight line scan. So this is the first characterization scan we typically take in these devices. Then the next thing is that once you have found one of these transitions and you tune near this one of these spots, in gauge space you need to find, of course, the right position where you can provide this gain. Okay? So what you do is, it's pretty easy to find the load and the empty spots, right? Like you can sort of easily stay away from that. From this point here, you sit somewhere over here or somewhere over here. But the exact read level is more difficult, so you fix those two and you start scanning this level. So this is the typical scan you take. You take a time trace as you perform those 3 pulses that I showed before. And this is an average trace, so each line here is 120 averages. And this is the first important result, I would say, from this line of research from 2010, done at about 5 Tesla. So the spins are really properly Zeeman split here. And well, you start here at the top of the scan. The read level is too high. So what happens here is that you put an electron on the donor, but then you are way too high and you always tunnel out, meaning that you immediately ionize the donor again and current is always on in the read phase. So regardless of the spin state, you have current and the donor is ionized. Oops. Is it stuck? Oh, Windows is deciding to do things. No, it's my laptop going bananas.
Okay.
There we go. I think PowerPoint just crashed.
Ah.
It does that. PowerPoint doesn't agree with reading out spins. All right, where were we? I think about here. There we go. All right. So this is how an actual current trace can look. This is one of these current traces. So during the load phase, we start with current, but then we put the donor into the neutral state. So we don't have current anymore, and then almost immediately after you put it in the read, you get current because you tunneled off the donor onto the SCP island. That's typical current traces. Then we sit here when the ground state level is near on resonance with the reservoir. The electron basically can randomly tunnel on and off the donor on the time scale of this tunnel barrier between donor and SCP island. And then in the measurement you see that as random telegraph signal basically. So you have these random spikes of current and no current, and yeah, that's typical examples of that. And then this is the area where you are at the right level, because now this one can tunnel off and you tunnel back on with the other spin species. Okay, so the average traces here, they show at the beginning here this current spike corresponding to this tunnel event, and then it is blocked again because you tunnel back on with the other spin species. So, and that is, so this measuring such a trace for the right time scale, that depends of course on the tunnel time scale, you need to characterize that. But this is an example of a spin down trace. This is spin up, spin down, spin up, another spin down, spin up, spin down. Just a number of examples. That is how that looks like in experiment. So we measure, we look for these current blips. And this also immediately determines the bandwidth that we have. This is a direct current measurement, so yeah, depending how accurate and fast you can digitize that signal, that tells you the type of tunnel rate of the donor you can work with. All right.
How fast is it down for the donors?
Sorry?
How fast is it down for the donors? Because
Sorry, just a second.
quite amount of time to wait when it's tunneled back.
Yeah, so this is, the time scales here are, I would say, microseconds to milliseconds, more milliseconds regime. It's not a very fast measurement.
Okay.
Not particularly fast.
And what is the waiting time?
I'll show that in a second. Sorry, my laptop is playing up again, I'm distracted. The phasing time of the electron, the T1, is very long. Basically, it's order 1 second, or 0.1 second. see if this. I'm really having a Windows issue here. Sorry for that. My other team member, I complained too much about. Let's try again.
And change the slides here, it doesn't change on the screen.
Now we have my screen again. Yeah, no, it's just PowerPoint or Windows doing weird shit.
It's possible, just,
You know what I will do? I will start turning Wi-Fi off.
okay.
At least no interference. Let's try that. All right. So this was the final case I showed you. There we go. Let's hope this was the last incident. Yep.
Why there is a current when we empty, if there is like spin up, it's just...
Yeah, because when we do the empty level, we put both donor levels far above the reservoir, so there is always a tunneling happening. And the way we operate the system is that when the donor is ionized, the current of the SET is on. So current means donor ionized, no current means donor neutral. So here, for a short amount of time, the donor is ionized because the electron could tunnel off, but then within the gamma of the tunnel barrier, another electron tunnels back of the other spin species. So mind you, well, this is a parallel setting, right? So when we have the current on block, many electrons pass, and then there's always one of spin down that can tunnel back onto the island. So you tunnel out with spin up, you unblock the current, many electrons pass by in that time, spin down tunnels back on. That's a stochastic process, of course, determined by the tunnel barrier of the donor to the SET, what the tunnel strength is. Okay? So this is, yeah, I think you could in principle also tune it the opposite way, that there is no current and the donor is ionized. But let me think. I don't think it's going to work. You don't want all these electrons passing by, then you have your new donor neutral, I think.
But then you will know when it's like stuck. Like it's passing, and then when it's...
Yeah, that is what you know now. Now you know when its current is passing through the SET, and the moment one tunnels back onto the donor, the current is blocked again. So this tells you current switching off means the donor is neutral. Okay, and then when you are too low, of course nothing really happens, right? Like there is this, you don't have this clear signal that you observe here. There's of course always some dark counts here, but this is the signal you look for, this clear, bright current peak. All right, and then you observe this boring trace. Now, you can use this measurement immediately to do a spin lifetime measurement, so that is a T1 measurement, and simply by adjusting the wait time here, you can get that out. And what you observe is that the spin up fraction, because this measurement here gives you averaged over many shots, it gives you a statistical spin up fraction, and in, when you have truly random loading, this should be about 50%. And when you repeat that after an initial wait time, you should observe a decay. The excited state should slowly decay to the ground state. That is indeed happening. This is measurements for various magnetic fields. And what you observe if you then, so as a function of the wait time, you can see that the time scale here is really 1 second. So the T1 time of the system is long. And what you see is you get this decay, the relaxation rate, 1 over the relaxation rate. It gets longer and longer at low magnetic field. And you can sort of see these two rough trends in it. And theory sort of suggests that you have a B to the 5 dependence here because of spin-orbit coupling in the high magnetic field limit. And in all fairness, why exactly the T1 is limited at the longer time in the longer time scale at low magnetic field, it's we have some theories about it, but we are not fully certain, I would say. So originally was that there's spin diffusion happening towards other donors, but I think it's a bit of a long shot, that explanation. People in the team were investigating if it could be Johnson noise on the gates, on the metal gates nearby, but this never got truly clarified, I would say, what caused this. I think this is still sort of open. It could be charge noise in the system. Anyway, T1 of, for an electron, a T1 of almost a second is more than enough, right? Like, we need to worry about T2. That is the message here. All right. Of course, now there's one thing left. This was the readout. Now to initialize, we need to adjust the load level properly as well. Because we were doing the read level, we found it by just making sure you load any electron. Now we need to also put the load level right in between the two states. There's an extra pulse here that we put in for basically technical reasons here, so you can pretty much ignore it, I would say. But because it shows up in the data, I have to show it to you. Yeah, the idea is now that we keep the empty pulse fixed and the read pulse, we also keep it fixed at the right level. And now we're going to scan the position of this one here so that we can adjust it and that we have the right spin loaded into the system, because we want to have control over that, right? Initialize it into spin down, for example. Right, so here you see it happen. So as we scan here the load level, you can see that in this regime we were higher than the read level, so there was no electron loaded. And then during the plunge, it was loaded. So you have this quick ionization happening. Now, this is the position where you want to be. Here, you have put your load level right in between the reservoir's level, so you tunnel on with spin down, and that means when you now put in the read position, you will not tunnel off. Okay, because the read position is in the same configuration, so this electron is now stuck here, it cannot tunnel off. So the absence of this bright line that you see here tells you there is no electron here that can tunnel off. Okay? So no spin-up states detected. And when you put it to low, then during the load phase, both of the species can tunnel on, and then of course you get also a spin-up fraction there. So this plunge here, in this scenario up here, because you pulse very deep and the donor was empty, you do load an electron, that is why you see this bright line over here. Alright, so this is how we can read out and initialize the electron spin of the donor. And this is single shot, right? Like this is, yeah, within your instrument limitations, we can do this single shot. This scan also allows you to already estimate the Zeeman splitting of the electron spin, because this is the length of this. Oops, the length of this section here corresponds to the Zeeman splitting in the system. So you need to convert the gate voltage into energy, which we can do, and you can fit that. And then as a function of magnetic field, this is not the best way to estimate it, to do it, but this is a way to already get a handle on the G factor, and you can see that, you know, it's more or less true. Within the resolution of the measurements, this is an electron spin. Okay, that was the readout and initialization. Now to control the spin, we need, of course, to be able to drive it. And for that, we need to extend the device and add the microwave antenna next to it. Okay? So now we have here the device evolved. This is 5 years later or so, a couple of years later. So we have added more gates. This is now the microwave antenna. Over here we have the SAT for the readout, and rather than a single gate to adjust the donor potential, we have split it in 4 individual gates so to have more control, basically more control nodes. This is built on a silicon substrate, and you can either use natural silicon or you can use isotopically purified silicon, and this becomes very important for the T2 of the system, and I will show you that in a second. So I can already tell you that it's absolutely pointless to work on natural silicon. There is like 5 or 8% silicon-29 left, and these nuclear spins completely dephase the electron spin. In terms of Hamiltonian, this is the effective Hamiltonian. I think it's highly accurate. The only difficulty is in the hyperfine interaction, that is like always slightly more complicated than putting it as simple as this. But for all intents and purposes, this is the Hamiltonian we work with. So we have Zeeman splitting of the electron spin with the electron gyromagnetic ratio. We have Zeeman splitting of the nuclear spin with a nuclear gyromagnetic ratio. And then we have the drive field. So this needs to be a broadband antenna where we can apply drive frequencies in the appropriate range for an electron spin and for a nuclear spin. So electron gyromagnetic ratio is about 30 gigahertz per Tesla. For a nuclear spin of phosphorus, it is about 15 megahertz per Tesla. So the antenna needs to be able to go up to tens of gigahertz, which is the tricky bit, I would say. Megahertz driving is always much easier. All right, and then this is the corresponding level diagram. So we have our donor somewhere sitting there, and this is how we operate the system now. So the hyperfine is now perturbation from the perspective of the electron. So we operate it in the limit where the Zeeman field is much stronger than the hyperfine interaction. So for that you typically operate at 1 Tesla or so. Hyperfine interaction of phosphorus donors is around 100 megahertz. So at 1 Tesla or more we are at 30 gigahertz in terms of energy for the Zeeman splitting, and then this is a perturbative term, meaning that we can treat this as two well-separated spins, so an electron spin and a nuclear spin, and we have two ESR electron spin resonance frequencies now. One, the bare electron spin resonance frequency minus half the hyperfine one plus half the hyperfine. You can see it already happening here, is now we have a conditional pulse that we can apply. So conditional on the state of the nuclear spin, we need to apply a different drive frequency. And then of course here we have NMR, nuclear magnetic resonance, and in the case of the neutral donor then we have the hyperfine term as well. So now we have half the hyperfine minus the nuclear Zeeman splitting or plus the nuclear Zeeman splitting. So this is 50 megahertz minus 15 or plus 15 at 1 Tesla megahertz. Okay? So these are 4 unique frequencies that allows us to drive these various transitions and control the system. So now it's a matter, if you do this continuous wave, you can measure a resonance peak, of course. If you do this in a pulsed fashion, you will measure pi flips, if you time it right, or Rabi oscillations. So the idea is that you apply this ESR pulse, and you tune the system to sit in between the Fermi level of the reservoir. You have loaded it with a spin down, then you apply this conditional ESR pulse. If you now measure a tunnel event, so you measure your little blip, you have read out the electron spin, but also immediately the nuclear spin state, because it responded to this ESR pulse. If there's no tunnel event, you know that we're in this initial state, or you have projected it into this initial state. Okay? So this is how the readout works. And then this is why it's so important to work in silicon 28. This is the resonance line width. So of this one of these ESR transitions, and you can see it's 1.8 kilohertz. This is at 42 gigahertz. So this is like an extremely narrow peak in terms of spin resonance. And it's also reflected when you do it. So when you make Rabi oscillations, so you vary the pulse length of your microwave drive, you can see that we have these beautiful Rabi oscillations. It's reasonably fast, right? It's whatever, less than a microsecond for a pi pulse. This is in silicon 28. And this is what we got, or the people before me got, when they used natural silicon. So it's really a difference of day and night. So it's barely possible at all to see electron spin resonance properly in natural silicon. So you really need to work in isotopically purified silicon. You don't need much, about 50 nanometers or so, on top of the substrate is enough, because the donors are very shallow, maybe 100 nanometers, but you need it. Then finally the ionized nucleus, so we can also perform NMR, of course, on the ionized nucleus, so really look at a phosphorus 31 nucleus spin, and now we only use the electron as a readout tool, so we only let it tunnel on to read out the nucleus spin. Then our Hamiltonian is only, all that's left is the nucleus spin terms, and this is, the T1 is unmeasurable. It is basically an event to be discussed over a coffee break when the nucleus flipped because of a real decay. It happens very rarely. And this is the T2. So this is done, this is using dynamical decoupling, so this is using all these pi pulses, and then you get a really long T2, in that case, it's of order 1 minute. The T2 star or the T2, the Ramsey T2 time or the Hahn echo is more of the order 100 milliseconds, 1 second. Okay, so it's an extremely coherent object. The absolute time scale is very long. Of course, one thing to always keep in mind is that it's also very slow to operate, the nucleus spin. Right? The Rabi frequency is much slower than that of the electron spin. It is of the order of 10 to 100 kilohertz at best. So in terms of how many operations you can perform, you are still looking at a number of like 10 to the 4, 10 to the 5. And then if you do dynamical decoupling, it can be even longer. So I still think it is an excellent qubit, one of the best around in the solid state. But never forget that nucleus spins are slow to operate. Then before the 5-minute break, it's raining outside. Whoever's going to smoke will have a hard time, I'm sorry. I want to quickly comment, and then after the break I will shift to a different type of nucleus spin, but now I want to quickly comment on the quantum computing perspective of the system. The big problem here is, the big open question is how to couple these donor electron spins in a controlled fashion. So we have a number of options. The one is that 2 of these phosphorus donors are sitting so close that they basically share the same electron. Okay, and then this has been demonstrated, beautiful experiments have been done. Of course, like, how can you cannot keep doing that, right, for many in a row or many in a lattice. So this is not scalable at all. You can do this for like 1, 2, 3 nuclei or so, but that's about it. Then this was the intended, in Bruce Kane's original proposal, this was the intended way. Have 2 donors sit near each other, let them both have their own electron. The wave functions of the electron overlap a little bit, so for that they need to be about 50 nanometers apart or so, or 10. And have exchange interaction between the electrons and have gate control over the exchange interaction. I think this is also hopeless, and we all kind of agree about it. Why? Because this is sensitive almost to the lattice side what the exact exchange interaction is. And that has to do with a property of silicon, that the wave function oscillates very fast because you're not sitting at, you're operating at finite momentum. So when you have fast oscillations on both of these wave functions, you get destructive or constructive interference, meaning that almost to the lattice side, you get a very different exchange interaction. And yeah, even with STM lithography, we don't have that precise of a control. So this can work at the level of, unicorn device, find maybe 2 or 3 donors that are coupled this way where you can have fun experiments, but this is also not scalable. The next idea, which is at least on paper the most feasible, is that rather than have exchange interacting coupled things, you have a gate on top that pulls the electron really away towards the interface. So you form a quantum dot state here and the donor state here, right above each other, and with the gates you can either put the electron on the donor or on the electron, and this creates a large electric dipole. An electric dipole coupling is relatively long range. It is of the order of 100, 200 nanometers, and this is tolerant against placement of the donor, exact placement. So this idea, I think, has solved these issues here, that you don't have control over the exact placement over the donor. But the big issue here, and this is ongoing research, but I must admit that it's been very difficult so far to make progress, the donor potential is so very steep that it is very difficult to have a nearby quantum dot well controlled and really have control over the exact shape and position of the wave function. So basically what I'm saying is it's almost impossible to create this system. At least this far it has not worked well. I think that is the most promising route to investigate it. And when this can be done and controlled and repeatedly with high precision, I think there's some hope that you can scale this up. Questions? I thought of putting a break here. Is it clear? After the break, I don't want to talk about the readout anymore, basically just look at spin physics of the nuclear spin. Excellent. And then we have a 5 minutes break, I suggest, and we continue after that.